All right. Let's look at the multiplication method. So division method, multiplication method. All right. Remember, the main goal of our hash function design, okay, other than fast calculation, the most important property we need, break any pattern in the data. That's the main goal. Break any possible pattern in the data. All right. So how do we break the pattern? So in this new method, we want to use multiplication way to break the pattern. Okay. So how can you do that? So let's see. Yeah. So here we choose a constant a. Yeah. And we set a in this range between 0 and 1, a small positive number, not integer. Yeah. Then we define the hash function in this way. Here you can see. So what's that? Yeah. M slot number, right? We know there are M slots, M slot number. K, the key value, times that positive constant. So you get a, usually it's not an integer, right? So a number with fractional part. Then you model 1. So you remove the integer part. You only keep the fractional part. Okay? All right. So the fractional part, that's the one also between 0 and 1, because it is a fraction. Okay? So you use that fraction to multiply m. Yeah. M multiply a fraction, so you get a, usually it should not be an integer, right? So integer with its own fractional part. Then you take the floor function to remove the fractional part. So you get an integer. Okay? Think about it. So here we tried very hard. Okay? We tried very, very hard. The goal is to break any given pattern in the data. Okay? Hope this method works. Yeah. There is a good chance it works. Yeah. All right. So now, if it is good or not, it depends on how to choose this a constant. If you choose a good one, then it works well. If you choose a bad one, it does not work well. Okay? Yeah. All right. A good selection of A can break most patterns. Yeah. Okay. So what is a good selection? Yeah. Our idea is use an irrational number. I hope you know it, irrational number. Okay. A number with infinite decimals, but there is no cycle. Yeah. You know, rational number, irrational number. So no cycle in the infinite decimals. All right. So pi is one example, pi. All right. But here, someone recommend this golden ratio. So we're familiar with the golden ratio. The golden ratio is a good candidate. Excuse me. Yeah, good candidate. Phi equals 1 plus square root of 5 over 2. That is this number. But we want a number between 0 and 1. So we don't need this 1. Okay, so we drop that 1. So we use phi minus 1. That is our A. Okay? That's a good candidate. Although there are many other candidates we can use. Okay? think about, how about pi minus 3? Can we use this? Pi minus 3. Okay. How about e minus 2? Right? E minus 2. Is that a good candidate? Right? How about 1 over pi? Okay. Yeah. How about 1 over e? Right? How about 1 over phi? Right? So all these numbers, so we can use. Yeah. All right. A perfect hash function. Now let's look at if we can get a perfect hash function. So what is a perfect hash function? Okay. So it should have this property: always map 2 keys to different slots. 2 different slots. Always. Okay? No matter what keys you pass into the hash functions, you can always get that. Okay? That's impossible. That definitely, so nobody can design such hash functions. That's impossible. Okay? So that means there is no perfect hash function. It does not exist. Perfect hash function. So you can only expect to get a hash function that works well for most of the time. Okay? Works well based on our 3 criteria for most of the time. Not 100%. You cannot expect works well 100% of the time. No. Okay? All right. Next, we need to look at the collision problem, because 2 different keys may be mapped into 1 slot, then a collision happens. So we need to handle that. Okay? So 2 keys are hashed to the same slot. Collision problem. Okay? All right. So the conclusion: no hash function can avoid the collision problem. So you always need to handle collision problem. You always need to have some strategy to solve the collision problem. Okay? Yeah. Here, let me talk about the first method to solve the collision problem. Resolving collisions by chaining. We use chaining method. So you create a chain. When a collision happens, you put those keys, items, mapping to the same slot in the chain. That's the first idea. Yeah. Assume that multiple keys are hashed into the same slot. Okay? For example, so we have a table here. For each slot in the table, we associate with the chain to store all the keys, all the items that are hashed into this slot. Okay? Associate each slot with a linked list. Here we need to use this data structure, linked list. Okay? Yeah. For example, like this. Okay? There is a linked list. Okay? So you have a chain. When you use linked list, you have a chain. Okay? Sometimes the chain could be quite long. When you have that situation, your search performance will be very bad. Okay? Yeah. All right. The longer the linked list, the poorer the overall performance. So that's why, so this idea has its problem. Okay? Yeah. Long chain problem. Okay. The worst case efficiency, big O of n. Very bad. Okay? Big O of n. The best case, big O of 1. Okay? The average case could be bigger of 1. Yeah. Because you take average. Okay? Yeah. So you consider the data, because the typical data we have in the real world, so they will not follow any specific pattern. Yeah. So then the probability to have long chains, not very high. So after you take the average, so you can get a relatively good performance. Yeah. All right. Measure average number of elements in a chain. So we need a special measure for that. So that number can tell us how well your method works. Yeah. So that number is called a load factor, alpha. We use alpha. Okay. All right. The meaning of the alpha, a hash table T, we assume there are n slots and n elements. So we need to distribute m elements into m slots, n elements into m slots. Okay? So we do simple division. Alpha equals n over m. N over m. That's the load factor of your hash table. Okay? So for this alpha value, it reflects the average number of elements in the chain. How long is the chain? So the average length. Okay? So the average length of your chain. Okay? So this alpha number could be in 3 cases. The first one, less than 1. Okay? Because your n number is smaller than m number. So you get an alpha number less than 1. Equal 1, n and m are the same, equal to 1. It could be greater than 1 because you have more data items than the number of slots. In that situation, on average, each slot, you need to have more than 1 data items. Yeah. So all could happen. Yeah. All right. So when you use this chaining method, when we have our data following the simple uniform assumption, here, we call it this hashing in this situation, simple uniform hashing. Yeah, but because the data distributed in a uniform way, it follows uniform distribution. Under that assumption, then the performance is good for this method. Okay? Any given element is equally likely to be hashed into any of the m slots. Okay? That's the assumption, okay? Uniform assumption, independently of where any other elements have been hashed. Yeah, so no relationship. Okay, yeah, independent way. Yeah. For that assumption, the average case efficiency can be given as big theta of 1 plus alpha. Yeah, 1 plus alpha. Okay, 1. So you need to map to the slot, find the slot first. When you go to that slot, right, the first time you spend this 1 operation, right, then you need to go to the chain, right? So then you need to spend this alpha on average, alpha number of times operation. Okay, that's why you have this 1 plus alpha as your efficiency description. Yeah. All right. Next, resolving collisions by open addressing. open addressing. All right, so here we are not using chaining. So chaining, yeah. The second method, different method than chaining, yeah. Open addressing. Yeah. So why we need to use a different method? Because the chaining way, we need to use a linked list. We know usually the linked list data structure is not that convenient to use. The overhead is relatively big. The overhead of a linked list is relatively big. So most of the time, people like to avoid using linked list data structure. Right? So that's why our next method, we use open addressing. So we use array, still use array, and we do open addressing. Open, okay? Open way, okay? So you can place your data element anywhere in the array, anywhere. So no limitation, no restriction. So that's the open addressing, okay? Yeah. All right. Let's look at this method. Do not use the linked lists. Elements only occupy the table slots. So that's array, typically. So slots, so we use array to model the table, hash table. Okay? And no space outside the table is used. Yeah. But for this method, we have one requirement. The alpha, the load factor, must be less than or equal to 1. Otherwise, you can overflow. Okay? Yeah. So you have to enlarge your array size if you need to store more data items. Okay? Yeah. Question. In this new consideration, how to handle a collision? Yeah. The idea. Straightforward. Find the next available slot. When you have a collision, you cannot place your data item in that particular location, but you need to find the next one. Okay. So, but what is the strategy? What is the method you want to use to find the next available slot? So there are many different ways to do it. Yeah. So in our next part, we will discuss several methods we can use to find other slots to place our new data item. All right, so we complete this part, 8.3.